All right, good afternoon, everyone. We'll go ahead and get started. First, I just want to make sure my mic's working. If I can get a confirmation in chat from someone. Okay, looks good. All right. So this course will look further into Slurm scheduling on the faster cluster. So this is an overview of what will be covered today. We'll look at what is an HPC, what is the architecture of the HPC, what components are part of the HPC. We'll look at the SBatch parameters. These are the parameters that Slurm reads for scheduling a job. And then we'll see examples of single node and multi-node jobs. And for the single node jobs, we'll show you how to run software that only uses a single core. And for software that supports multi-core, we'll show you how to configure job scripts for that. We'll have a break somewhere in between there. And for multi-node jobs, there's different ways you can configure multi-node jobs. There's MPI jobs. That's for software that supports MPI. If you have hundreds or thousands of commands that run on a single core, you can use CMU Launcher or Job Array to handle those jobs, and you can run those across multiple nodes. And we'll also look at monitoring a job as it's running, and we'll look at how to monitor the resources that the job used, and also we'll look at some of how to debug some failed job issues. All right, this is an image of the faster cluster, and you can see the description down at the bottom. 184 nodes. There's a lot of these nodes have GPUs installed. We'll look at how to see how many GPUs are available on how many different nodes. This is a composable cluster, so the number of GPUs per node could change. If you have a request, if you request a certain number of GPUs and there's not a configuration available, then there's ways to add certain number of GPUs to a compute node. So we'll talk about, I'm using the term node, nodes, cores, and queue. You'll hear that throughout the talk. So a node can be considered a computer unit of an HPC cluster. Each one of those contains memory and a CPU, kind of like your desktop computer or your laptop. And there's generally two types of these nodes. There's the login node and the compute node. So the login node is where you stage your job scripts. Whenever you access the cluster, you land on a login node. And from there, you use your favorite text editor to edit text files and create job scripts. And you can use Unix commands also to create job scripts. Compute nodes, sometimes we'll just refer to these as nodes. Jobs are only scheduled on the compute nodes. Many of the compute nodes on Grace contain GPUs, and we'll see how to list those. Using more than one compute node is based on how you configure your job script or how the software supports running on more than one node. A core, these are also referred to as CPUs. Faster compute nodes have 64 cores, and these are 256 gigabyte memory nodes, but only 250 gigabytes are available for jobs. The other 6 gigabytes, that's reserved for the operating system on each node. So you can use all 64 cores in a job script, but that's purely dependent on whether your software supports multi-core processing or if you configure your job script to use 64 one-core processes. Queue, this is an ordered list of scheduled jobs. You'll see jobs in the queue that are pending and running. Individual queues are also termed partition. You'll see the word partition in some of the output. Example partitions you'll see on Grace of the GPU and CPU. A CPU partition is auto-assigned when you configure your job script, but if you want to use the GPUs, you'll need to specify the GPU partition. I'll show you how to do that. All right, this is a typical HPC diagram, you see the login nodes on the left here. Depending on how big the cluster is, you might have 1, 2, 3, or more login nodes, and this distributes the workload across multiple nodes. Let's just say you had 100 users all logging in, and if you only had one login node, they would all be on login node 1, and some users may be testing software, and some may be using a lot of memory, and it can slow down the processes. A lot of processes can slow down the compute node, the login node. So that's why we have more than one login node to distribute the number of users across the login nodes. So the login nodes used for file manipulation, creating job scripts with your text editor, or if you upload, when you upload files to the shared files system, you can access these through the login node. Short tasks. If you want to test software, as long as it doesn't reach the 60-minute mark, any processes that reach 60 minutes are automatically stopped. So if you need to do any processing, if you think it's going to last longer than 60 minutes, then you should use the compute nodes for those. Create a job script and use the compute nodes, and use a max of 8 cores. This is across all of these nodes. Doesn't mean you can use 8 cores on each login node. Max of 8 cores across each. Compute nodes. Lots of compute nodes. Some have CPU only, some have GPUs attached. Both the login and compute nodes can access the shared file storage. This is where you run your computational jobs, where you can use all the cores on the compute node, all 64 cores, and up to 250 gigabytes per node, per compute node. These are for jobs that are running longer than 60 minutes. If you're not sure how long your job will run, you can configure it to run for 2 days, for example. And when it completes, if you recognize it only took about 2 hours to run, then next time you can schedule it for 12 hours. Give it a little buffer room there. All right. So how do we access the login nodes? It depends on where you are. If you're on campus, you're connected to the campus network, you can use the portal, or if you have a SSH client on your computer, if you have Mac or Linux, I think the Windows PowerShell may work also. You can access the login nodes this way. If you're off campus, you'll need to connect through the university VPN, the virtual private network, and then you'll reach the campus network, and then you can log in either through the portal or SSH client. Access users, they will use either one of these. So on your login node, this is where you create your job script. This is an example of how the workflow for creating a job script. You submit it to the Slurm queue, and then it might be pending for a minute before Slurm finds resources for it. It depends, depending on how busy the cluster is, it could be pending for an hour or more. Then once the processing is done, the output files are saved. And this is on the shared file system that we saw earlier. So when you're working in one directory, the files created can be printed to that same directory. So accessing the portal. So what we're going to do today is access the portal using access the command line using the HPRC portal on Faster. So what we're going to do is go to portal and go to Faster portal. And if you're an access user, you can go to Faster portal for access users. All right. So if you do have a SSH client, these next couple of slides are for how to access using the SSH client, and that's just a terminal. It's called a terminal. Notice that login sessions that are idle for 60 minutes will be closed automatically. And remember that processes running longer than 60 minutes will get automatically stopped. So on the Faster portal, we can go to Cluster, Faster Shell Access, and use your A&M password. And whatever form of Duo that you have. And then what you'll see is you'll see a message of the day. It's good to read this because what you can see right here is there's a faster cluster maintenance coming up tomorrow. So this means the clusters are unavailable from 9 in the morning till 8 p.m. It also shows you your quotas. Check these. If you're having problems with jobs running, check these to make sure you didn't reach your quota. I've still got plenty of space here as far as the disk quota goes, but there's also a quota for file count. So a lot of users will reach 1,000 files in their home directory, or 10,000 files. Actually, I think it's 10,000 files. Whatever your limit is in your home directory, if you reach that amount, then a lot of jobs won't get scheduled. That's more information if you're using the SSH terminal, or there's other clients you can use, Mobex term for Windows. It doesn't matter which login node you land on most of the time, but just you can see what login node you land on by looking right here. So this is the login node Faster 1. Okay, so now one thing you might want to check when you first log on is to see how busy are the clusters. So what I'm going to do is I'm going to move this over to the side. So you Control L to clear the screen. So if you type sinfo, this will show you the partitions or the what we also call queues. So the CPU partition, GPU partition. Some of these are not available to all users, but this is the part you can see how busy it is. It might be a little difficult to translate this, but there's a little map here. So A is active, I is idle, O is offline, T total. So for the CPU nodes, there's 112 total, 22 are offline, probably having some maintenance done. 7 are idle, and 83 are active. They have active jobs. So there's 7 available idle or idled CPU nodes right now, and there's 7 idle GPU nodes. And the same goes for cores. So we also have a handy little tool that will summarize the available GPUs and the configuration. The configuration could change. So tap in GPU avail. It will show you the current configuration. For example, this will show you how many GPU nodes that have A100, that have 4 A100s installed. There's 3 of these nodes right now that have 4 A100s installed. There's 8. So there's 1 GPU that has 8 A100s installed. So this is how it's configured. These numbers could change. For example, there's a lot of T4 nodes. There's 29 T4 nodes that have 4 T4s installed. So what about the availability of all of these? So these are the ones that are the individual nodes that are available. So if you look at GPU node, this is the node name. So if I wanted to use an A100, there aren't any A100s available right now. That just means that they're being used by other jobs. You can still submit your job script and Slurm will schedule it, but it will remain in the pending state until one of the A100 nodes become available. So if I wanted to run this and it didn't matter to me which type of node, which type of GPU was on the node, I could go ahead and configure my job script to use a T4. There's 4 GPUs on this node and they're all 4 available. So if I've configured a job script with 4 T4s and submitted it before anyone else right now, most likely my job would land on on this node or maybe this node. So it just shows you that there's some T4s available. This A30 is available. It has 2 GPUs installed and 2 are available. However, even though this says compute node FC100 has 8 GPUs installed, it says there's 4 available. However, if the other job scripts running on here have already used up all the memory or the cores, then these are not going to be available, even though they show up in this table. It's just a little bit more difficult to pick those out. But this is just a reminder that even though there's 4 available, they may not be available, but due to the other jobs using all the cores on that compute node. All right, so this is what a job script looks like. It's just a text file. It has some Slurm parameters. Those start with #s_batch. And then you can put comments, just like in any bash script, comments, and then Unix commands. Any command that you would run on the command line, you can put that in your job script. So this is, you can see this is the specific command or parameter to specify a job name. With a job name, you can put whatever you want. Just keep it short and concise. And if you want, I recommend avoid using spaces, but if you want to use spaces, you'll need to put quotes around your job name. The format is days. So it starts out with days, dash, hours, minutes, seconds. So generally you can just easily go from 1 day to 7 days if you just use the days placement here. So how many nodes? By default, a job script will request 1 node. So you can put 1 on here if you want. If you later think you want to scale this to multiple nodes and you want to test it on 1 node first, it would be useful to put that and test it with 1 node. And then you can just go back and change this and to run on more than 1 node. Tasks per node. So what is a task? So think of task as a command. For example, the command here would be the spades command, spades.py. So how many spades.py commands am I going to run in this job script? I'm going to run just 1, just this 1 line right here. So the number of tasks per node is 1. How many CPUs am I going to use for that task? Just 1. And then you'll see also some software called CPUs threads. So threads, you'll set that to 1 to match the same as CPUs per task. And then the amount of memory, you'll request the lowest amount of memory to charge for 1 service unit, and that is 3 gigabytes. And we'll go over increasing these in the next few slides to get more memory and more cores. So the first thing you want to do is module purge, and this will assure that anything that you put in your bash RC will not get loaded into your job script. And then you'll load the appropriate modules. And then you can run your commands. You can have several commands, several lines here. And if you need to, you can, after this command, you can module purge again and load a different module and run a different command if you have a workflow. So you can purge and load modules throughout your job script if you need to. As far as naming your job script, you can call it whatever you like with whatever suffix you like. .job, .sbatch, .sh, .slurm, those are the common ones that users use. I just recommend you be consistent because you may want to find all your job scripts and copy them to a directory to back them up one day. So if you name them consistently, then it'll be easier to find your job scripts, whether they all end in .job, .batch, or start with a string and end with a string that you can match. All right. There's a lot of information on this slide, but mainly this is going to be useful as a reference slide. I'll go over these quickly. These are the commonly used 1 nodes. Again, it's optional. You just basically increase the number to use more nodes. Make sure your software supports running on multiple nodes before you select 10 nodes. Otherwise, you'll be running on one node, and the other 9 nodes will be idle and not available to other users, but you'll still be charged for those other 9 idle nodes. All right, pretty much defaults to 1. Everything pretty much defaults to 1, like n tasks. If you say n tasks equals 1, that means the number of CPUs per task will default to 1. And number of nodes defaults to 1. N tasks per node used together with CPUs per task. So actually this should be tabbed over. N tasks per node is 1 and CPUs per, okay, CPUs per task. CPUs per task, 64. No, this is correct. Just that you would use these together. How many tasks per node and how many CPUs per task? This is useful to do it this way. Otherwise, when you start to use multiple nodes, you have to do some math calculations based on how many nodes you're using and how many CPUs, how many tasks you have and how many CPUs per task. It's sometimes easier to use the per node or per task parameters here. So example, in the previous slide, it was spade was the command or task. In this example, magic glass is the task. You can set the number of threads to 64, and different software will have different ways to call cores or threads or CPUs. In this case, this software uses -num_threads. All right, time, you'll have to put a time. How long do you want to reserve the resources? Start out with hours, minutes, seconds, or you can start out with days, hours, minutes, seconds. So the max runtime currently is 7 days for a job. Memory, you'll need to define how much memory you want to reserve. If you want to reserve all the memory, just use 250G. Otherwise, if you're not sure how much memory your job will use, still go ahead and use 250G, and then afterwards you can search to see how much memory your job used. So in the future, you can reduce the amount if needed. Because if you start out with 3 gigabytes and your job ends up requiring 10, your job is going to fail. And then maybe you go and increase it to 5 and it still fails, and 7 and it still fails. So it might be easier to start from the top and work your way down. Okay, job name, give it a job name. Output and error. These are useful for separating the standard out and standard error into separate files. You can have them saved to the same output file if you do it in this format, if you just use output. All right, partition, this is like the queue, the GPU partition. You'll need to specify that when you're using GPUs, but you don't need to specify CPU partition. If you want to use GPUs, you have to use this --gress. This is a way to request one of the T4 type GPUs. So the GPU partition, the type of GPU, and the number of GPUs. So these two lines go together. You need to put partition equals GPU also. If you want to use an account other than what is your default account, you can put this in your job script, account equals, and the account number. You get the account number from running the my project command on the command line. The default account is used if you don't set it in the job script. If you want an email when the job starts, when it ends, and if it fails, you can add these 2 lines here. Just remember that if you're configuring a job to submit 10 more job scripts, then you're going to get an email for each of those job scripts. So just be aware of how you configure job scripts, so you don't get 10 or more messages from the cluster. This is one that might be useful. It's definitely optional. If you run a job script and you want to run a second job script, but only after the first one completes successfully, then you can use this dependency after OK, and then the job ID of the job you just submitted. All right, submitting. There's different ways to submit jobs. You can do this on the command line in the directory you're in. You just type in sbatch and the name of your job script. And this will submit the job script. You can also use the sbatch directly to inside this job script. This has all the sbatch parameters for time, job name, memory. You could do this sbatch on the command line and specify the time, number of nodes, job name, memory, and output, and your commands that you want to run. But you don't have as good of a history of what you did when you use a job script. You can run interactive jobs also. This might be good for testing software. This will basically take you to a compute node. From the login node, you run this and it'll take you to a compute node, and then you can run your jobs here. Just remember that if you configure one CPU per task, that when you test your software, you're only using one CPU. And there's a lot more parameters you can add in your job scripts here and environment variables. All right, service units. You'll hear us say SUs a lot. How do you get more SUs? Actually, we have that on a few more slides later. Right now, what is an SU? For the faster 256 gigabyte memory nodes, there's 250 available. So if we look at this, this is one service unit. It's calculated as one service unit per CPU per hour. Is charged one service unit per CPU per hour, or one service unit per 3 gigabytes, or 3,700 megabytes. But Slurm doesn't accept decimals, so you either have to use 3 or 4, or you can do 3700 M. But it's just as easy to do 3G in your configuration, and then increase it to. You can calculate 3,3700 megabytes times the number of cores, and then convert that to gigabytes. You can do it that way. That much memory per hour. So if we look at this table, if you request 1 core and 3 gigabytes of memory, you're not requesting any GPUs. This is for 1 hour, then you will be charged 1 service unit to start that job. You submit another job, 1 core, 4 gigabytes of memory, no GPU, 1 hour, you'll be charged 2 service units because you've just passed a 3,700 megabyte or 3.7 gigabyte mark there. So if you could select all of the memory and just 1 core, no GPU, for 1 hour, you'll be charged for all 64 cores. So configure all if you're going to use the entire compute node, configure all 64 cores, all the memory. For 1 hour, you'll be charged similarly to this. For GPUs, for example, if you have 1 core, this is the number of cores on CPU, 3 gigabytes of memory on the motherboard, and then for the GPU, you select 1 GPU. If the configuration is like this, there's an A30 that has 2 GPUs and you're only requesting 1. You're not using all the memory, so you're only charged. So for the A30 GPUs, you're charged an additional 128 service units. So it's 128 plus the 1 for the single core, that's 129. And the reason is because someone else can use the other GPU on this node if you don't use up all the memory or more than half. So what if you do use all the memory and all the cores, but only one of the GPUs? There's 1 GPU there that can't be configured for a different job because there are no CPUs or memory available. So you're going to be charged for both of those GPUs. It's 128 times 2 plus the 64 cores for the CPU. So be aware of how you configured the memory and select the number of GPUs. A lot of software, well, I don't know about a lot, but some software that runs on GPU may not need a lot of memory on the motherboard or a lot of cores. So you could start out by just using half the cores, half the memory, if you're using 1 out of 2 of the GPUs. All right, single node job. When do you use single core jobs? When the software only supports commands using a single core. Or a multi-core, usually if you type in the software command and type in -- help, it will show you if threads or CPUs, if there's a way to specify a number of threads or CPUs, then you can add this to your job script. But there's some software that doesn't allow you, that will use multiple cores, but doesn't allow you to set it. It will basically just search for how many cores are installed on the system and use all of those. So be aware of how the software runs and use multiple cores, if it does at all. And if the software supports multiple cores, go ahead and use an entire compute node. For example, if you're doing sequence alignments, use them all. Use all the cores. Get the job done quickly. That's the purpose of an HPC, is to use multiple cores. Get the job done quickly and move on. Otherwise, use one core. It could take. It will take longer, and you may get charged the same number of service units in the end. All right, faster nodes have 64 CPUs, 250 gigabytes of available memory. And if you have a lot of single core commands, you can group those into a multi-node job with TMU Launcher. We'll show you how to do that. Here's a couple of examples of job scripts. This is just similar to the table that I showed earlier. If you configure one job with 3 gigabytes, 1 CPU, you'll be charged 1 service unit. If you configure 1 CPU and 4 gigabytes, then you're charged 2 service units. Make sure whatever value you put up here in the CPUs per task, that you match that value down here. And I'll show you a variable you can use down here so that it will read whatever's up here. So any unused service units are automatically reimbursed. So if I submitted example 1, I would be charged 1 service unit. If it's for 1 hour, if it completed in exactly 30 minutes, I would get half a service unit reimbursed back to my account. Same goes with the large jobs. If your job is charged 10,000 service units and you only used half, then you'll get reimbursed 5,000. All right, end tasks. Some people use end tasks as a quick way to just specify the number of cores per tasks. If you say end task equals 1, then everything defaults to 1. The nodes, CPUs, tasks, CPUs per task all default to 1. If you say end task equals 64, nodes is 1, CPUs 64, num task 64, and each of the tasks use 1 CPU. You can do it that way, but when you start to scale across multiple nodes, then you have to do some math. So how do you use all the available memory on compute nodes? For a CPU only node, these are ones that do not have a GPU attached. 64 cores and 250 gigabytes. So 64 one task per node, or one task per node, 64 CPUs for this single task, 250 gigabytes. You can reverse these. You can say 64 tasks and 1 CPU per task. For GPU node, the same cores and memory are available. And the way you do that is you specify the GPU name here. Use the lowercase. Uppercase A will not work. So A100, A10, T4, all these characters are lowercase. And then the number of GPUs that you want to use. And make sure you include this make sure you include this line, this whole line here. Similarly for the CPU only, this is for the motherboard here. So you can configure one task, 64 CPUs per task, 250 gigabytes of memory. Okay, this is just to kind of reiterate what I mentioned earlier. If there are 4 GPUs attached to a node, for example, if you run GPU eval and this GPU has 4 nodes attached, and there's 3 of these configured on the system. Here's one here that has all 4 available. So what you want to do is you want to request no more than 1/4 of the CPU and memory, so that other jobs can use the other GPUs. If you only want to use one GPU. Now, if you schedule, so here's an example of taking 1/4 of the resources for one GPU on a node that has 4. If you request one GPU, look at the second point here, and you use all the cores in memory, the other GPUs are unavailable to other jobs. So you will be charged for all 4 GPUs. Just keep that in mind. So here's the summary. 16 cores plus 64 charging for the single GPU. So you'll be charged 80 service units per hour if you use this compute, if it lands on this compute node. This is another one. Basically, just to get an idea of if you requested all the memory, but only one GPU out of 4, then you'll be charged for all 4 GPUs, right? So you'll be charged first 64 for the CPUs, and then how many GPUs? 4 times 128. So 4 times 128 plus 64. That's 576. You'll be charged, if you configure it this way, you'll be charged 576 service units, even though you're only using one GPU. So just be aware when you configure CPUs and memory that you'll be charged for all the GPUs if you request all the memory and CPUs. All right. This is different ways to configure the different types of GPUs. Basically, just do T4, A100, A10, A30, A40, and N will be the number. If you put 99 here, it will not start because we don't have a node that has 99 T4s on it. So the numbers from 1 to 8. Currently, that's the number at the time I made this slide. So this could change. So these numbers may change. So you'll need to check the configuration with the GPU eval command to see how many T4s, the maximum number of T4s on a single compute node. But we do have we have 200 T4s on the cluster, on the whole cluster. So there's more T4s than these A-series GPUs. All right, here's a couple more examples with job scripts. Basically just reminding you, if you select all the memory, but only half the cores, you will be charged for all the cores because the other cores are not available to other jobs because you've used up all the memory on that compute node. So go ahead and configure all the CPUs, all the memory, and make sure you match any CPU or threads or core option in your software command to whatever you have up here. All right, you can use a Slurm environment variable. This variable is only there whenever you submit the job. It's not available when you first log in on the login node. So when you submit your job, this will be populated with whatever is in your job script. So Slurm CPUs per task will take the value here, and if you use it here, it makes it, if you have like 10 commands and each one has a threads option and a value here, instead of changing this from 1 to 64 in all of your commands, if you do it like this, then you only need to change it up here once, and it will be available to all of your commands down here. All right, multi-node jobs. So multi-node jobs, you change the number of nodes to 2. And then if you use this per node approach, then it actually makes it easier to scale across multiple nodes. Otherwise, you have to do some math if you're going to say number of tasks and you're going to distribute all those tasks. So when you say in tasks, that's the number of tasks across all the compute nodes. So instead of trying to figure that out, it could be easier just to take the per node approach and just multiply by the number of nodes and increase this number as needed. So you can see I'm using all the cores and all the memory on these nodes. It's actually better to use an entire compute node than use half of 2 different compute nodes. So these are just different configurations. If I say 2 nodes and 64 tasks per node, then I'm actually going to be requesting 128 CPUs, right? Because 64 on each of 2 nodes, 128 tasks, each task using 1. So 250G, that's always a per node. That's always per node. So you don't have to multiply memory by the number of nodes. This is the memory parameter is always per node. So what you want to be aware of is this last one here. So if you say I want to run 2 nodes, a job using 2 nodes and 64 tasks, this will allocate 32 cores on one node and 32 on a second node. And if your software does not support running across multiple nodes, then you're going to have one node that's using 32 cores, and the other node is unavailable. So these 32 cores are idle for the time, the duration of your job. And so these are service units wasted. So be aware of how you configure if you're going to use in tasks together with nodes. If you are using multiple nodes, make sure the software supports multiple node processing or that you've configured your job script to use multiple nodes. All right, here's just an example of multi-node software. Selecting 10 nodes, 1 task per node, 64 CPUs per task, 250 Gs. Probably should have put 64 tasks and 1 CPU per task. If that's the way this software is going to be running, maybe it's going to be running 64 tasks and each task runs 1 CPU. But you might find different ways to actually specify the total number of processes or cores and the per node number of cores. So in this case, NP is a way to, when you use NP run, NP is the way to specify total cores across all nodes. That's basically taking the number of tasks times 10. In per node, the number of cores per node is 64, basically taking how many tasks per node, 64. You can see when you start to scale it up for multiple nodes, you start to use up require a lot of service units. All right, this is the best, looks very similar. The best just uses the different options here are ways to specify the total number of cores and the number of cores per node. So whatever, depending on what the software, how you run the software, you may have to configure these differently, or they may have different options. All right, TAMU launcher. This is a way if you have hundreds or thousands of commands that use a single core, instead of running one command and waiting for that one to finish, then running the second command, waiting for that one to finish, that's just not a good way to configure your job script. So you want to run as many at a single time as you can, on as many cores as you can. So you might can do that easily on one node, but what about when you want to use multiple nodes? Well, you can use TMU Launcher to distribute single core commands across multiple nodes. And a good thing about TMU Launcher is, let's say you've configured your job script for one day, and after one day you've only completed 50 out of 100 commands. Then the next day you can just submit the same job script and it will pick up and start with command number 51. If you use a job array, you will have to look and see which commands were completed before you restart your job. So TMU Launcher is a good way for restarting jobs. All right, so how do you use TMU Launcher? You'll have one file that has all the commands in it. So this is just an example. You have 500 commands. Here's the top 40 or so commands. And you can see each command uses one core or one thread. So just a text file. And in that same directory, you have your job script. And in your job script, you will say, I'm going to use 2 nodes, 64 tasks per node, and each task is going to have 1 CPU, because that's what we have over here. So 1 CPU, and we're going to reserve all the memory because we're reserving all of the cores. All right, and then you'll need to just have one job script, do the module purge, load your required module. This module is going to get loaded and available to each one of these commands. So what this is going to do is you have 64 times 2. You're going to have 128 of these 500 commands that are running. And whenever one of these commands completes, it will pick up the next command and run it. And it will continue until it completes all 500. All right. What if your commands run can use more than one node or more than one core? And then you can increase the number of cores per command. You can still use TMU Launcher. You'll just need to configure your Slurm parameters a certain way. For example, we're still going to use 2 nodes, but this time we want to use 16 tasks per node and 4 CPUs per task. So this is CPUs per task. So it's going to use 16 spades commands per node. So it's going to be running 32 commands at a time across 2 different nodes. And when one of those 32 completes, it's going to start command number 33. So that's the way that works. So configure this. This is important. If you are using a command that uses more than one core, you'll need to configure the Slurm parameters accordingly so that it does match the number of tasks per node and the CPUs per task. Some software does use this OMP num threads environment variable. This is for OpenMP. If the software requires this, you may not find out until after you run it, and for some reason it was only using 1 core out of 10 or 1 core out of 4. Then check the software, or just go ahead and set this. The default is 1, so you can go ahead and set it to match CPUs per task. And that way, each of these commands will be able to use more than 1 CPU. But most of the time, you don't have to do this. But rarely, there's some software that has this and they don't tell you about it. This is just a way to create those commands that we saw earlier. So you can copy and paste this command. It may work, it may not. Sometimes a dash is not transferred correctly to the terminal, especially when you're working with browsers on those. So the second part basically creates a bunch of empty files that we can use as input. So what we want to do is we want to create a commands file that, kind of like we saw in the previous slides, where you have 100 or thousands of samples, and each sample you want to run a single command. So these are this is just some practice to show you how different ways you can use shell commands to capture values and variables and manipulate the variables. So if you just go work through this, all right. So you can see these are the files I created. So if I say no space there, seeks S1, R1. All right. So you've just created a variable called file, and the way to see what's in that variable, use echo and a $sign with the variable name. Otherwise, if you just say echo file, it's just going to echo the word file. So $sign is used to show you the value of this variable. So next we want to take a command called base name. So but what this does is strips off this whatever absolute or relative path you have. It strips off the path to your file and just gives you the file name. Okay, so let's use another variable, the third one here, the fourth one here, sample equals. Now what this does is you're running a command, a $sign open parentheses, you're running a shell command, and you're capturing the output of that into a variable called sample. So the previous command we ran was just base name of the file. Now we're going to run this command again and capture that into a variable called sample. So you can see now we have a variable called sample that just has the sample file name. We still have the variable file, and it has the path to the file. Okay. So now what we can do is, if we just want to capture the sample name, which is S1, because you can see the samples are named S1, S2, S3, 3, 4, all the way to what did we do? 40, sample 40. So we want to capture the sample name. So that's what the next command is for. Go. So $sign braces, what this does is takes a variable and allows you to strip off some of the part of the value in the variable. So you can see I was able to strip off this underscore r1.fastq.gz part and just capture the sample name, sample 1. Okay. And then what you can also do, notice how I did // here to do the removal part. So this removes this part. If you want to do a replacement, then you just do R1 1/R2. What this means is whatever matches R1, replace it with R2. So now you can see the sample is sample 1 R2 .fastq.gz. So with these functions, or these Unix commands, you can actually do quite a bit with manipulating the value within variables. So we learned how to create a variable, strip off the path to it, a variable if it has a file name. Then we use this how to run a command and capture the output into a variable. And then we learn how to actually manipulate the value within the variable. This just echoes the value. It didn't actually change the value. The sample's still the same, even though we echoed the part, we stripped the part off of the sample here. It didn't change the value of sample. So now you can do this. This was how to do a for loop. So you want to loop through all of the samples, and it just so happens that this example, there's 2 files per sample. So the way to do this is do a for loop for file in. This is the way you capture. We just want to capture the sample name one time, so we're only going to capture the R1, the files that have R1 in it, and then we're going to capture variables, manipulate the variables, get the base name, and then we're going to echo the actual command. Depending on how many sequences there are, we'll echo that command that many times, and then at the end we're going to redirect the output to a text file. That's what this last part is. So basically you can just type this in, and notice that when I type that line in, now I get a different prompt. It lets me know that I'm continuing within the for loop until I type in the word done. Read one, substitute. Don't forget to close parentheses. So what I did here is, if you want to take the value of a variable and add more text to it, you'll need to put that variable in braces so that you can add underscore out or continue with starting with alphabet characters, alphanumeric characters. All right, so now you can see I created my commands file. So you can work through that. This could be a lot easier once you get the hang of it. It'd be much easier than using an Excel sheet and trying to move that back to the cluster, and then you end up with some weird characters in your JavaScript files. But once you learn some of these few simple shell commands, it makes it very useful. So here's another one. If you want to try this, we're just going to take a break here, and you can work through this on your own. Here's the commands. Here's the outputs. When you type a command in and there's no output, that just means there's no errors. But basically what you can do is you can strip matching different substrings and stripping either before or after that substring. It's a little more complex. This is a kind of a table I use, and I use it as a reference whenever I'm trying to create something more complex. So that's just here for your knowledge, and you can work through this during the break on your own. All right, we're moving on. Slurm job array. Job array is a way to run a single job and allow that job to run across multiple nodes, and allow Slurm to configure how many nodes the job is configured to run across. It could also be used for running multiple commands on a single node, depending on how many cores per command is being used. You just use the -- array and specify the number of arrays you want to use. You can start this if you have 24, if you want to use 24, if you have 24 jobs or 24 commands to run, you can specify 0 to 23. If you want the index to start with 0, if you want it to start with 1, you do 1 to 24. You can specify indexes comma separated, or you can use a dash to indicate I want to go from 1 to 7 use a colon and step of 2. So it'll submit a job array where the index is 1, the next one is 3, next one 5, next one 7. So this is actually going to submit an array of 4 indexes. You don't need to use nodes with array. Slurm will handle that. All right, so basically you can tag the array, the task ID onto each of the output files. So this could be good also when if you want to say, I want to run an array of 40 indexes or 40 commands, but I only want to run 5 at a time. So this is a good way to limit the number of files that are written. Let's just say you're running software that creates 100,000 temporary files when it runs, and then it deletes them when it's done. If you run 40 of these commands all at once, you're going to reach your quota, your file quota, and then your job's going to stop, and then you got to clean up everything, figure out what completed, what didn't. But you can limit that to only 5 of the 40 commands running at any one time. So this limits the number of temporary files if that's an issue. Here's an example. If you use array 1 to 40, running only 5 at a time, using 5 entire compute nodes, or using all the resources on each of 5 compute nodes, you'll need a commands file that you can use similarly to the commands file we created for TMU Launcher. Use the same type of commands file, basically just a command, 1 line per command. And then you actually need to run this a different way. Instead of doing TMU Launcher and your name of your commands file, if you're doing an array, you would do command equals. Then remember, this is how to run a command and capture the output of this command into a variable. So this is a command you're actually running. Task ID, remember, this is from 1 to 40. So basically what you're saying is use this sed editor, take out line 1P. This P is the way to indicate for sed to take out line 1. So show what's in line 1 of this file and save it to this variable, and then run that command. This might take a little practice to get used to, but once you understand this, it can help you run jobs better instead of submitting. It says some users will submit 1 job script that creates thousands of job scripts, and that's not the way to do it. You'll want to either run all these commands in a single job script and distribute it across multiple nodes, a certain number of cores per commit task, or you'll want to use a job array or TMU Launcher. These redirectional operators do not work with this approach because of the commands in your file has the operators in it. So you can use a task ID. For example, if you have sample 1, sample 2, all the way to sample 40, you can capture using the variable slurm array task ID as part of the sample name. So you know the file name sample. For example, the first array is going to run sample 1. And remember, we use these braces if we want to append anything before or after the variable name. So we're going to capture, when this command actually runs, it's going to run sample 1 underscore R1 fastqgz, sample 1 underscore R2 dot fastqgz. And you don't need to create a commands file if you do it this way. Basically, this single command is going to be run on 40 different nodes. And this is something I haven't shown yet, but if your command is really long and it scrolls across the screen, you can make it easier to read if you end it with a backslash. It's backslash because it's leaning backwards as we read. Just make sure you don't put a space after here. If you put a space after this backslash, this command will fail. So make sure there's nothing after this backslash. All right, here's some other variables you might find useful. Temp directory, temp dir. This is a So this is a local disk. When I say local disk, I mean that this is a disk that's plugged into the compute node directly. It's not going across the network to the Scratch drives. This is plugged into the motherboard, so it's directly connected. It doesn't have to go through the network, so it's a lot quicker. It is a NVMe drive, like the solid state drives are. They're a lot quicker, and some software can run a lot quicker if you use this local disk instead of writing across the network, especially if you're writing thousands and millions of files, writing and deleting thousands and millions of files. If you write this to the local disk space, it's going to speed your job up. Or if there's some temporary files and you can specify this with the software, you can put that as part of the command. For example, in this samples command, if I'm going to do a sorting function, and then I can specify, do the sorting in this temp directory. So all the files that are during the sorting process are written to the temp directory. When the job is over, the temp directory gets deleted, and any files in the temp directory never count against your quotas. So if your quota is 250,000 files and you have software that's going to write 2 million files, instead of requesting a quota increase, you can use this temporary directory to write all these temporary files. They don't count against your quota, and it will most likely be quicker than trying to write a million files across the network to the Scratch space. CPUs per task, we saw that a couple of times. You can use that in your command to capture whatever you put in the Slurm parameters. Task ID, that's to capture whatever number of arrays you've created. Job name, if you want to create an output file or directory in your command that captures the job name, this could be useful. Might be easier to recognize the output if you're having multiple job scripts in a single directory. If you need to capture a node list of all the jobs that ran on all the nodes that were configured for your job, you can capture those jobs in this if you output this, the output of this variable. Now, all these variables, again, are only at runtime when you run a job. There's not a temp dir on the login node. This gets created and destroyed whenever a job is started and ended. Slurm job ID, whatever the job ID is, you can capture this if you wanted to make it part of your output directory or your output files, file names. User, this reflects your net ID. If you echo user, it will show your net ID. Scratch is the way to, it's a variable that has Scratch user and your net ID. So you can say CD Scratch like this, CD Scratch, and it will, you will go to your Scratch directory. We talked about this. You can set this. If you export OMP num30 is equals 64, that will be exported to the commands, any commands that your job script runs. PWD this might be useful if you need to capture or create output files or directories. You can use this command or this variable. All right, so now we want to go over actually running a job script. So we talked a lot about configuration, and let's not open a text editor and create copy and paste or try to create our Slurm parameters and find some software. We have other tools, other short courses that show you how to search for software, also how to run this, some of the software, specific software. So what we'll do now is we'll use this GCA templates tool, and basically this has a lot of template scripts with job scripts that are already pre-configured with some example data. So you can get an idea of what a Slurm job script looks like. You can run it, you can watch, you can monitor the job running, look at the output, see how it works. And then later on, you can spend time on learning how to edit the Slurm job parameters and creating your job script. But this gives you an idea of how the job scheduler works. So what we'll do is go back to it. I'm going to Control L to clear the screen. You'll probably just move this to half. Okay. So now I'm going to make a directory. All right, make directory. And then I'm going to cd to that directory. All right. So now I'm in Slurm class. This is just a directory with nothing else in it. You can type in GCAT, hit tab, and it will complete for you. Right now, we've only got very few of these template scripts, but we have a lot on Grace if you're using Grace, and we'll be moving those or copying those or make them work on faster in the near future. So what I want to do now is look for a tool called BB Norm. So you can do S for search for BB Norm. Oh, it didn't show up. So let's do one. Oh, it's BB map. So I'm going to go back home. Exactly search for BB map. I need to update this slide. Okay, search BB map. Okay, it takes you to BB map. So now the tool is BB map. You might see tool BB map version 3896. You might see another one that was created 3 months ago, and it's using version 38.24, for example. So you pick whichever version of the tool you want. Let me go back home because I wanted to show you. You can, if your idea is to trim FASTQ file, you can go into that directory, and then we're going to error correct normalize, and then you come to the same place, BB map. So you can either search, if you know the tool name, you can search, or you can go through the category task tool. So now option this, there's a job script configured for paired end libraries. You might find one configured for single end libraries. We only have one job script option in this case. So the script is called run bbmap version 3896 bb norm faster.sh. So that's the name of the job script. Do you want to copy it? Y for yes. This is a reminder. It's just a template script. You need to update the SBatch parameters. Search the software to see if there's any options that you need to use for your data, or increase the value or decrease values or change the values of any of the options that are already in this. So we will see what this is like on, we'll cat the output to the screen. So you can see at the beginning, we have this already configured with Slurm parameters. It's configured for 1 hour, 1 task, 64 CPUs per task, and all the memory. Module purge, it's loading the BB map module. There's some comments in here, shows you where you can find the user guide. It tells you this will error correct and normalize FASTQ files to a targeted coverage. So you can change the targeted coverage if you want. But for now, this example just is set to 75. Max memory, you'll probably want to make the max memory equal to this or less. But I just have it set it to 50. Output files, so you'll see the input files. There's already some example input files. So this script is ready to run. The commands are actually here. So I haven't gone over it yet, but there's a tool called job scripts, and that will show you the CPU and memory, print the memory usage of your job script over the duration of the time that your job runs. Here's another command that tells you here's the first command that's run. This is the error correct command. And then the second one is the normalization of the error reads. So you're taking the output from the first command, using it as input for the second, and then you'll create a graph. And then, as always, we have citations. Don't forget to cite us if you publish, and also do not forget to cite the tool if you publish. It helps for the tool to maintain funding if they're cited. So we've got a job script. Now we want to submit it. Submit your job script. You just use SBatch and the name of your job script. Now I'm going to hit run and hit tab because there's only one file there. So SBatch run. And after I hit that, after I push enter, I want to type in SQUE-U user. That will show me. That will show you the job status. Right now it's pending. It's looking for a CPU node that has 64 cores and is pending. The reason is because it's checking for resources. You can do up arrow and run that again. It's still pending. So there's still resources. So I'll show you later, but if your job's pending for hours or a long time, it could be for a number of reasons. We'll go over that. But one is right away, you notice there's a maintenance tomorrow. Today's the 7th, February 7th, tomorrow, February 8th. So if you're, let's see what up arrow. Oh, it's still pending. So let's type in there. If you didn't have this message on your screen, if you had already cleared it and you're working and it's still pending, you can type in the command maintenance and it will show you how many hours until the next maintenance. So there's a maintenance that starts in 17 hours. It'll last for 11 hours. So I configure this job script to run for 1 hour. So the maintenance is not interfering with my job script, because if it launches now, it only runs for an hour. I'm not reaching into that. I'm not reaching that 17 hours from now window. So maybe it'll start soon here, still pending. All right, we'll let that get started and we'll keep going. So you can cancel a job if you want. Use scancel and the job ID. So whatever job ID you get from here. This is actually, let me make this bigger so we can read the columns better. All right, the job ID is here. If I wanted to cancel that, it's still pending. I would just type in scancel and the job ID, but we don't want to cancel this. So keep it in the queue. All right. Once your job is running, you can use the PEStat command to check on the CPU load of your running job. So let's just say you're using all 64 cores and you want to see if your job is efficiently using 64 cores. Or maybe you didn't configure your command correctly and it's only using 1 out of 64. So if you notice that and it should be using all 64, you can cancel your job and then make the changes and run it again. But just be aware that sometimes a software will run to use all 64 cores. Then it will run another step that only uses 1 core. And then it'll switch back and run all 64 cores. And this PEStat is updated every 3 minutes. So if you run this and then you wait a minute and run it again, you might get the same value. So you do have to wait a while till it gets updated. But just because it's showing you that you're only using 0.01%, or the load is 0.01 out of 28 cores you reserved. Actually, this is a CPU load for the entire node. So this is really only useful for these first 2 because you know that your job requested all 64 cores and this job is almost using 64 cores at 100%. This one's close, but not quite 64. So that's why it's purple. If it's underutilizing the number of cores, you'll see it in red. Might not be an issue for GPU queue because most of the processing may be happening on the GPU. So this actually is fine that it's using almost no CPU load, because if you were to go to this node and look what processes on the GPU, is probably the GPU could be at 100%. So, oh, now the job is running. Okay, this job lasts about 5 minutes. It's already been running for 1 minute and 43 seconds. So let's go to the PEStat. So here's the job. I've requested all 64. Since this gets updated every 3 minutes, this may not be accurate since I just started the job. So we can check back in a little bit. Okay. S-control show job ID. This is only available. This is only available The way I did that is I double clicked this and then hit Control V to paste it. So this is only available when the job is running. So if you want to, you can add this at the end of your job script, and you can output all of this information. Basically, it shows you, it has a record of how many CPUs, GPUs, nodes. It shows you the directory where you submitted, the work directory. It shows you the command, which is the job script. This information might be useful in the future. But once your job is complete, you can't run this anymore. So let's go up arrow and see if our job's still running. It's still running. We got a couple of minutes left. Okay, SEFF. This shows you the memory efficiency, CPU memory efficiency. If I run it now, it's going to say, warning, efficiency stats may be misleading for running jobs. So it really can't get good stats until this job is over. So when this job is over, then you can run SEFF for the job ID. And this is good for, this will be kept in memory, or this will be kept in the database. So a month or 2 months from now, you can come back and still check. If you wanted to, if you're checking back on some jobs you ran, you want to see the memory efficiency, then you can see this command is still available, but scontrol is not. So when this job is done, we'll check it again. Still running. And we'll review that. Okay. Job stats. This is, I showed you it, or I mentioned earlier that it will keep track of the CPU usage and GPU usage if it's a GPU job. And now it will also track the IO of the temp directory. So in this case, this is not a GPU job. Notice it's in the CPU partition. But if you were to run a GPU job and you requested 2 A100s and you ran your job and then you ran job scripts, you have to do job scripts and before you run any of your commands. So it'll do the monitoring. And then when you create the graph, if you see this graph, the GPUs are actually numbered 0, 1. So the first GPU 0, this GPU, you can see the load is red. So 100% load is what we want to see. And then the gigabytes of memory, that's how much memory it's using. So it didn't use it. It was probably using CPU on the motherboard and the memory on the motherboard. And then it started to use the GPU. And then it went back to the CPU and then it used GPU. So this GPU is being used, but this second GPU has 0 usage all the way across. So you basically, this tied up this GPU with an idle job. It didn't use this GPU. So in this case, if this happens, you can run SEFF on this job, see how much system memory and CPU you used, and see if you can get by with only using half the number of cores and half the memory. That way you configure half and you leave this GPU available for other users and you don't get charged for this. Otherwise, you're being charged for both these GPUs, even though you've only used one. All right, let's see if our job's still running, still going. All right, you can read about that and see some more information in job stats. So talked about service units. And this will show my project -J all will show you all your jobs that you ran for the current fiscal year. It does take a few days for jobs that I run today to show up. So as soon as this job is done, if I run this command, it's not going to show up on the output. But this is good because it does show you the for each job, it shows you the used service units. So how many were you charged? And then you can get a total usage of service units. Okay, this job's still running. So if I exit this right now, if I exit this terminal and leave and come back, everything's still running. The jobs are still running, and let's see there are some files getting created. It's still in the error correction step. So it's still going, still got a second step. So it looks like it's going to take longer than 6 minutes. I thought I had it running for 6 minutes, but we'll let that keep running. Okay. So something I did mention, I may have mentioned it. Yeah, you get service units reimbursed for unused time, even though it's scheduled for an hour. If there's 30 minutes left, I get reimbursed for those 30 minutes when the job completes. So service units, debugging job submission. So this is when I actually did the S batch and the name of the job. So you might see this error message right away and the job doesn't get scheduled. S batch CPU count per node cannot be satisfied. You probably put CPUs equals 1,000 or something like that. Well, there is no, and nodes equal 1 and CPU equals 1,000. There's no CPUs per node equal 1,000 or CPUs per node equals 100. There's no compute node that has 100. So Slurm says there's nothing here that matches what you're requesting, so we can't submit the job. So just check your SBatch parameters again and check which cluster you're on and make sure that you're not requesting more CPUs per compute node than are available. You may also get a message that says you don't have enough SUs for this to run this job. Your job requires 1,000 service units. You only have 500. So you need to get more service units. There's a link here that shows you how to get more service units. Basically, you ask your PI to allocate more service units from your PI's account. And then once you get a second account, then you'll need to change your default account. And you can do this with the My Project SD and the account number. So first run My Project, you'll see your accounts. This is just showing you that my default account is this first one. There, I was given 5,000 to begin with. I've already used 4,999. I've got one service unit left. And then the second one was an allocation from my PI. And then my PI gave me, was that 10 million? 10 million service units. Very generous. So, but I still can't run jobs because default is for this account that only has a balance of one service unit. So I need to switch the default and so use this account, and it will change this to a Y, and that'll be a no. So now all your jobs will be using this account. It has 10 million in it. All right, let's check our job. I think it's still running. No. It's like the error correction part got done. So whenever one hint is whenever you're looking at the contents of your job script, your job directory, if you just list the contents over time, you're going to get more and more files. So you want to see which files are the newest. So if you do ls-lsth, it will show you the newest files on top. See, 1522. So this is the actual, I created the job script first, and then when I run it, it started to create all these files. This is the first step, the error correction. The second step is normalization. So now you can see the normalization file. It was 77 megabytes. Now it's 203. So it's creating this output file. Now it's 252. So it's still running. You can see file size is increasing. So it's doing something. It's almost done because this is the last step. Actually, the last step is to create a graph, but this is the last step of the computational part, is to create the normalized reads. All right. Pending jobs. My job was pending for a while. Was it because the cluster was busy? I can use sinfo to check that. our main website will have a percent node and percent core usage information on it for faster. That will be in the near future. If you're trying to use a GPU and your job's it's still in a pending state, it's not running, it's not in a running state, check GPU avail. Maybe you're trying to use 4 A100s, but all the nodes that have 4 A100s are not available. So run GPU avail. As they become available, they'll show up. So now we have an A100 that has 4 GPUs and there's 4 available. So now you can start your job and it'll probably land on one of these unless someone beats you to it. All right, let's see if our job's done. Our job's done because all we have is the headers here. So LSS, LSTH, there we go. Now we got a number of output files, error corrected. This is totally based on how we configured our job script. Output files, fastq.gz. That's the first step. There's some log files for job stats, creates the CPU and IO log files. If it uses a GPU, you will see a stats_GPU log file. But since there were no GPUs here, it only created log files for the CPU and the IO to the temp directory. Here's the standard out and standard error files that we configured in the job script. And then there's a couple of images here. So since we were writing information to the temp directory, we might be interested in the IO of the temp, of what was written to the temp directory. Sometimes it's just out of curiosity, and it might be useful for deciding whether or not to use the temp directory. Stat CPU, that will show you. I'm going to just go link us to the page. Job stats. So that will basically show you the CPU stats is going to show you the percent load on across all cores. This is best if this graph is most useful if you're requesting all the cores and all the memory, because this represents all the cores and all the memory on that compute node. And if you only requested one core, then there's other jobs that are counted as part of this percent load. So in this example job script, there is about 42% load on the CPU for most of the job, and then you can see towards the end it did probably some cleaning up and finishing up. The amount of memory went up a little bit, but it didn't use the max, which is about 250. If you're using GPUs, you'll get some graphs like this. This shows that the GPU is used pretty much the entire duration. During this part here for 45 minutes, GPUs are being used, and it looks like the CPU is doing some final configuration or final computation work here. Amount of memory fluctuated between 0 and less than 5 gigabytes. So this job actually had 8 GPUs, but there's only 4 showing. In the image, there's another 4 I didn't add on here. IO stats just shows you how many reads and writes to the temp directory, which holds the temp directory, temp dir. And again, this highly dependent on, only is most useful when you reserve the entire compute node. All right. So we looked at jobs not getting scheduled, pending jobs. That was now check the maintenance. If there's no maintenance and your job is pending, it might be because the cluster is busy or there's no GPUs available. So also run this maintenance command to see if there's a scheduled maintenance, or you can check the message of the day. And the way you check the message of the day is just MOTD. It will print that message of the day again. You can see we do have a maintenance. Or if you want to know how many hours until maintenance, because you want to start your job and you want to run it for 16 hours. So or you got 17 hours and 31 minutes. So if you submit your job for 17 hours, if you configure your job to run for 17 hours, and if it starts right now, it will work. But if the queue's busy and your job doesn't get considered until an hour from now your job is 17 hours and the maintenance starts in 16 hours. So just be aware that it may take a while for your job to start. So you might want to use 15 hours or just keep an eye on it to make sure that it does start before the maintenance. All right. If you configured 3 gigabytes of memory and your job reached that limit, you'll see an error that looks like this. Exceeded job memory limit at some point. So that most likely is you need to rerun your job, configure with more memory, and rerun the job. Resubmit the job script. If you're unsure, again, use all the memory and all the cores. Then when you're done, we can actually do the SEFF. So we're going to run SEFF on the job ID of the job we just ran. Okay, so we can see the job ID completed successfully. The exit code is 0. Exit code of 0 means there were no errors thrown. It's showing we configured all 64 cores. Now it's showing it used 30% of these 64 cores for the duration of the job. That's fine. You're probably not going to see 100% for the duration of the job because in this case, our job script, we have multiple steps. So some steps may have been using fewer cores at a time, and other steps may have used all the cores at a time. So as long as this isn't like 0.001%, and you configured all 64, then you're fine with that. Memory utilized 122. So we used about 50% of the memory on the compute node. So you may want to, if you don't want to use all the cores next time, you can configure it to use 48 cores, for example, and maybe 3/4 of the memory. But you don't want to use 50% because you're very close to 50% here. You don't want to go over if your next data set input files are larger than this one. But that gives you an idea of the resource usage for this type of input, this size of input files, this software running on this cluster. So this is very useful. All right. If there's no space left on device, you may have reached your disk quota, or the temp directory could have gotten filled up, which is a possibility because that's another device. So check your quota, show quota, and if your quota is 10 terabytes and it shows 10 terabytes of your disk usage, you cannot write any more files. So you'll need to reduce files size by downloading files, offloading files from the cluster, save them somewhere for long-term storage if you need them. Compress files, delete files you don't need, free up some disk space before requesting an increase in disk space, because increases are only temporary for the current project you're working on. Then you'll need to remove that project from the cluster. Clusters file systems are not for long-term file storage. So manage your disk space and file usage accordingly. All right, so reduce number of files you've generated. We did that. Not delete non-essential temporary files. Use the temp directory in your command. Very useful, unless your command uses checkpoints and writes down checkpoint files. You don't want those deleted when the job is completed or fails, and when a job stops. So depending on the software, you may not want to use the temp directory. Just be aware of how the software, where and how the software writes temporary files or the actual just output files. And then if you've already done all this, if you've deleted non-essential files, temporary files, you're just using temp directory, and you downloaded your other projects to free up disk space. Then if you need extra space, you can request a temporary increase. All right. So we talked about the portal. We're actually using the terminal on the portal, but there are other applications you can use. These are applications that have a graphical user interface. This is just a current list right now. There's some bio apps here, genome browsers. Then we have some other applications here. VNC is actually a way to launch a job on a compute node, and it actually just gives you a command line. So it's a command line. You can run commands on the compute node. You can close your browser and come back and open it on a different computer, and you're still your environment's saved. As long as the job didn't run out of time, your environment's there for you to continue working. So you could run a command, go home, log back in and check it again, check and see if it's complete. If it's done, you can end your job, just because you don't need to have a session idle using up service units if there's not any computational processes going on. You see monitor and stop running jobs and interactive sessions. There's a way to kill the jobs through the portal. All right. It's actually our last slide here. So this is just a listing. If you need help running anything, having any issues with configuring job scripts, job fails, you can't figure out why. We have a FAQ. There are some common problems: running out of service units, reaching your quotas, having hidden characters in your input files. A lot of these are common problems that we have. We have solutions on our web page there. Check the common problems wiki page and see if it helps. Otherwise, you can send an email to our help desk at help@hprc.tamu.edu, and then that will create a ticket, and that ticket will be picked up by one of our staff, and we can help you with that. In your ticket, make sure you leave us some information, which cluster. We have a few clusters, so it'll help us and save you time if you let us know the cluster ahead of time, because we may come back and say, well, which cluster are you using? So we don't have to go searching all of our clusters trying to find out which one you're using. Which cluster? Send us your username, your net ID. Usually that's in your email, but you can send us that. We don't need your UIN number. We don't need that. Send us the job IDs so we can run the SDFF command, and we can look for standard out, standard error files that match that job. Where is your job file? Which directory? And if your job fails, don't delete any temporary files if you want us to help debug, because we need those. There might be some log messages to help debug that. What software did you load? Are you loading anything? Are you running this on the command line? If you are, what are all the commands you ran? Did you do module purge first? Which modules did you load? Did you create your own special environment that we need to know about? Let us know what error message you're looking at, so we can start off in that direction. And then tell us what you've done. Give us a short description of what you've done, so that we can reproduce the error if we're unable to see it right away in the error logs. And then also let us know when the issue's been resolved, so we can close the ticket. Sometimes the user doesn't get back with us. We'll give them the answer and they don't get back with us, and then we have to send them another email saying, hey, did this work for you? And so once it's resolved, let us know so we can close the ticket. So that's it, and thanks for your time.